The title of my talk is Reconstructed High-Resolution Forest Dynamics and Human Impacts from Étangs-Fer-de-Lance, southeastern Quebec, Canada for the last 2 millennia. Our study site is located here in southern Quebec. It's in Mount Orford National Park, and you can see that it's surrounded by dark green, so forest, but this is secondary regrowth forest. And you also see that there's a number of towns like Granby and Magog, and also the city of Sherbrooke nearby, as well as a bunch of light green agricultural land today. The lake is about a kilometer long, and it's at about 300 meters in elevation. Here are our obligatory nice shots of our field site. It's in the Parc National de Mont Orford, which the park was founded back in the 1930s. The lake is cradled in between two mountains, Mont Chauve et Pic de la Horse. And just orient yourself, it's in the northern part of the Appalachian Mountains. Now you can see that here is the red star. This is our site. You can see to the west there's this pink. This forest type is the sugar maple bitternut hickory. This is the warmest type of forest in Quebec. And then as we move to the east, up in elevation, we hit the brown forest. All of these ecotones going on, changing forest ecotones going on in southern Quebec are driven by temperature. So in brown, we have the sugar maple basswood domain, which is where we're located in. And then if we move 50 kilometers further to the east, further up in elevation, we're into the Appalachians proper, and then we're into the sugar maple yellow birch domain. So we have two ecotones within 50 kilometers of us. So it's a relatively sweet spot to be doing high resolution pollen analysis. And then there's also the changes along the alpine gradient as well. So our research questions are, how sensitive have these sugar maple basswood forests been to climate variations over the last 2,500 years? In particular, we care about the medieval climate anomaly in the Little Ice Age. And we also want to know, have recent forest composition changes over the last, say, 200 years been within the region's normal range of forest composition change, or are they way off the map caused by direct human impact recently? So here is core information. The core is about 2.5 meters long. It's this funny black gelatinous gitcha. It's like hard jello. It's the weirdest stuff you've ever seen. We are able to well date it. We've got 12 lead-210 dates and 11 C14 dates on terrestrial macrofossils. They're mainly on birch seeds with a bit of wood. Here is our age depth model. Depth on the x-axis, calibrated years BP on the y-axis. The green is the lead-210 dates. The purpley blue is our radiocarbon dates. And you can see for the first meter plus, so for the first 1,000 years, the age depth model made by Bacon is pretty good. Fairly tight confidence intervals, things look good. Then we hit the first millennium AD, where our confidence intervals become much bigger, and our age depth model becomes less good, but that's what we have. It's the luck of the draw whenever you take a core. So our core altogether spans 2,400 years. If we look at the pollen summary diagram for Étangs-Fer-de-Lance, here it is right here, we have about 202 pollen samples, so an average sample interval of about 24 years. So 4 samples per century, so high res. Now, our dominant throughout this period of time is Betula, birch, and it doesn't really tell much of a story. Where the story is coming from is our 3 subdominants, Fagus grandifolia, which is American beech, Tsuga canadensis, which is eastern hemlock, and Picea, which is spruce. Here, this is a mixture of white, red, and black spruce. Conus and PCA divide our pollen diagram into 3 pollen zones. A pollen zone 1 that's split into 2 subzones. This covers the little bit of the BC the first millennium AD, the medieval climate anomaly. Then, starting in 1300, we have pollen zone 2, which covers the early part of the Little Ice Age. And then we have pollen zone 3, starting in 1600, which we're calling the human modified period. So pollen zone 1, this is, according to other regional high resolution paleoclimate reconstructions, this is the warmest period of time, and this is when the beaches when we have the highest abundance of beach. Then we move into the beginning of the Little Ice Age. As we do the transition from the medieval climate anomaly into the Little Ice Age, we've got a cooling climate. Spruce comes in. We've got significant increases in spruce, and we have significant decreases in the eastern hemlock and in the American beech. We also at this time have significant increases in Pinus heploxion, which is eastern white pine. And then in 1600, we move into the human modified period, which it's picked up by CONUS and by PCA. It's starting as a weird two-step ragweed rise. First of all, we start with this low increase, but it's a definite increase in ragweed and ambrosia, starting in 1600, that goes through until the fall of Nouvelle-France in about 1760. Also at this time, we have an increase in grasses, Poaceae, that starts in 1550 and that also increases. We think this early increase is a signal of Haudenosaunee agriculture from the Haudenosaunee Confederacy, who are located in upstate New York and in parts of Montérégie. Then with the fall of Nouvelle-France, we move into a proper ambrosia pollen rise, big bang of increase of ragweed, increase in grasses, increases in sedges, continuous decline in our beech, and in significant decline also as well in our hemlock. And we also see an increase in our weedy acer species. So this is a big increase in red maple right here, which is going on. We also have a reconstructed charcoal record in which we see 4 significant fires around the watershed of Étaing-Fer-de-Lens. The last one is starting at 1800, is probably European land clearance. These other ones down here, they could be indigenous agriculture or they could be natural ignition. We don't know. Montreal, yes, was founded in 1642, but for about the first 60 years of existence, it was a precarious military fort and fur trading post and smuggling post, and there really wasn't much human impact except on the island of Montreal. So we really think this two-step ambrosia rise, that first step, is probably indigenous agriculture. Then we do a climate reconstruction using modern analog technique, and we have a temperature reconstruction showing that we have a warm, and we have a precip construction, so we have a warm and dry first millennium AD, a slightly less warm and dry medieval climate anomaly, and then we have a really distinct cold and wet Little Ice Age. The top of the core, this is too much human impact, so in grayed out, you'll ignore it. And then we're using a squared core distance, and we look at how close our analogs are to the modern pollen training set, and they're quite good. By and large, they're within that 5% range. So we compared in nearby regional high-res sites that are 4 sites, also 4 sites or more per century. So this means we're comparing to Lac Brûlé and Noir of Conrad Gajewski, pollen reconstructed sites. Also Conrad's Clear Pond, Basin Pond, and Conroy Lake, also pollen. Kurt Steger's Wolf Lake, diatom inferred precip, and then a testate amoeba, Sydney Bog. There's other sites within this region, but they're not high res. So we see that we fit all of the sites that have a temperature reconstruction are showing this distinct warmer first millennium and then cooling from there, cooling into the MCA, and then real cold little ice age. So we're all agreeing with all of the regional climate reconstructions. We look at precip. Here we've got a different story. Most of the northern New England sites are showing what we see, a dry first millennium AD, a dry but slightly wetter medieval climate anomaly, and then a wet little ice age. We fit this regional pattern. We are not agreeing with Konrad Gajewski's Lac Brûlé and Lac Noir that show a wetter medieval climate anomaly and then a drier little ice age. This isn't that far away. It's in the Ottawa River Valley, on the, just in Ottawa, but this moving inland, we seem to move into a different climate regime. So just to conclude, we see definite forest composition changes over this last 2.5 millennium. We see the increases in spruce and white pine that are significant. We see significant declines in the American beech and the eastern hemlock. We're fitting our temperature and precip reconstructions are very similar, are exactly based to those coming from northern New England. So we're fitting into that regional climate pattern of becoming cooler and drier. So we think that this, not cooling and drier, cooler and wetter, this cooling and wetting climate is driving our changes in forest composition. And we also see this intriguing possible Haudenosaunee agricultural signal that we'd like to look at more in the future. So thank you very much, and I'm open to questions. Thank you. Bye.